So let's just talk again about where we are and where we're going. We have some point in the world. I'll draw my point in red. And that point is not going to move. The point stays put. And what we're doing is we have one coordinate frame. Maybe this is world coordinates, and I'll say that this is X of world coordinates. And so I can make this Y of world and this Z of world. And I'm just double checking again to make sure I got it to be a right-handed coordinate frame, and I did. And maybe I have a second coordinate frame over here that looks like this. So its origin is right in the middle here. Can you see that's the origin? And now I'm going to make, maybe X will be pointing up. So I think that means, yeah, that you can't see me, but I'm busy waving my hand around. It means we have X, Y, and Z here. And what I want to do is I want to say I have a point that's fixed in space. This point is not moving. I happen to know what its coordinates are in terms of world coordinates, but really I'm doing all my work. Maybe this is robot coordinates, and I want to know how do I get there relative to world coordinates, right? Or sorry, relative to robot coordinates, the X, Y, and Z of my robot coordinate frame. So that's where we're trying to get to. But rather than starting there, what we've done is we've started just by talking about doing frame transformations, right? Where we're trying to transform, we're trying to move one frame so that it aligns with another frame, and talk about how we do that. And so far, the only frame transformations that we've done are just a single, or not a single translation, but just translation along one or more axes, right? Just X, Y, and Z translations. And we don't have any rotations. All of our coordinate frames have X, Y, and Z aligned with each other, parallel to each other. So now for this lecture, we're going to start to talk about what is this relationship between this frame transformation that we've had a little bit of a glimpse into, and how we transform points from one coordinate frame to another. Right? Remember, when I say transform points from one coordinate frame to another, I don't mean we're moving the point. I just mean we're trying to figure out what is the coordinate, what are the coordinates of a point in different, relative to different origins and different coordinate frames. So what we're going to do now is we're going to jump into part 2 briefly here, and we're going to talk about, well, how do we do those kinds of point transformations, or transformations from one coordinate frame to another of a point where the point doesn't move. Remember, the point never moves. We're just thinking about it from a different perspective, and understand why this frame transformation thing that we've been talking about kind of helps us figure out what the point transformation is. And just to review, we're calling the process of how to align the K frame with the J frame the frame transformation that goes from K to J. And we're abbreviating it with this F, which is Dr. K's notation. It's not normal notation. I made it up, but I think it's helpful. And this is F from K to J. Well, I made the slide, so I'll say it. From K to J. And just in case you weren't listening to me, this is not a standard terminology, right? This is something that I made up, but I think that you will find it very helpful very soon. So let's talk about something that I didn't make up. We're going to start talking about homogeneous transformations, and we abbreviate it like this. It's the homogeneous transform from J coordinates to K coordinates. And this is what we're going to refer to when we talk about looking at two coordinate frames. So maybe I have, maybe this is my J coordinate frame, and I also have, right, so what have I got? X, Y, and Z. So there's X sub J, Y sub J, and K sub Z sub J, sorry. X, Y, Z, yep, that works. And then I have another coordinate frame somewhere else. Should probably put arrows on that. I have another coordinate frame somewhere else. Maybe we'll make it fun. We'll make this z sub k. So if that's z, z goes to x, right? So that's x sub k, and that's y sub k. And the idea is we have some point fixed in space, right? There's my point. And I already know the location of this point. I know it's XYZ relative to J coordinates, where this is 0, 0, 0, right? I can tell you where this point is located, but I actually want to know where is that point located relative to here. So this is the way X goes, this is the way Y goes, this is the way Z goes, and that's my origin, right? So if I want to take this point that I know in J coordinates and convert it into K coordinates, I use this homogeneous transformation, which we abbreviate T from J to K. I clearly went a bit crazy with my slides. So from J to K. So now I'm going to tell you something cool. This frame transformation that we've been talking about, that tells you how to transform how to move frame K so it's into alignment with frame J. Well, that actually represents a matrix, okay, a 4x4 matrix. And even better, this transformation, the homogeneous transformation from J to K, also represents a 4x4 matrix. And super exciting, these two matrices are equal. So if we can figure out the frame transformation from K to J, that will automatically give us the homogeneous transformation from J to K. So we can use the frame transformations to tell us how to figure out how to do this magical point transformer thing. And then there's these matrices. So I expect at this point you are saying, what the heck are you talking about? Where did matrices come from? As an aside, if you are a sufficient geek, this just suddenly made me think about this. You should look up Tom Lehrer, and you should look up his song New Math. That's the name of the song, is New Math. There's a line in there which says, where did we get 64? How did 64 come into this? It's very funny. Welcome to my trying to keep people awake doing slides. Anyway, we'll get rid of that. Here's what we're going to do. We'll work our way up to the matrices gradually. I need to first talk to you about how we're going to represent points as vectors. And once I've done that, I'm going to show you how we can come up with a matrix that we can pre-multiply the point by that will turn it into a different matrix. But I'm not actually going to tell you how I got the matrix. I'm just going to show you that it works. And then as my grand finale, I'll show you how to do that for any old example. So let's start by talking about how we're going to represent a point in space. We're very used to talking about a three-dimensional point by showing it like this. We're going to change our notation, so we're going to represent it as a vector where we have x, y, z. And then we're going to have a value at the bottom. Usually we're just going to write 1. That's the simplest way to deal with it. But it's actually a weighting factor. So all three of these vectors actually represent the same point. They all represent the point x, y, z, this point. And you just need to divide each element in the first 3 rows by whatever's in the bottom. And you find that you have the same thing. So that's what I mean by a weighting factor. And because it gets to take up a lot of space when you try writing these vertical vectors, we are often going to write them horizontally and just put the little t at the end to show that we mean transpose. So we will write this XYZ1 transpose that's actually the same as this. So let's take a look at an example of one particular matrix that actually we can use to figure out the location of a point in different coordinate frames. So here's an example that we did in a previous slide set where we were talking about figuring out the frame transformation. Again, how did I align the M coordinate frame, which looks like it's this one here, with the C coordinate frame, which is this one here. And we said, well, if I'm in M coordinates, then I need to align this, I need to go -5 units in the X direction, +4 units in the Y direction, and then up 1 unit in the Z direction. And this is the matrix that represents F from M to C. And you can say, well, that's very nice, but why the heck did you do that? And I'll say, because remember the super important point that we said F from M to C is the same as T from C to M. And so what's T from C to M? T from C to M is the matrix that if I know a point in C coordinates, it'll let me pre-multiply by this matrix and I can figure out what that what that point's location is in M coordinates. So let's do a couple of examples. Let's start by saying, what's the location of the point that's located at the C origin? What's the XYZ coordinates of that if I'm in M coordinates? I want to turn a point that I know in C coordinates, right? Because what is the address of that? The location of that in C coordinates? Well, in C coordinates, that's just the point 0, 0, 0, right? The origin. And I want to turn that into M coordinates. So here I've just written 0, 0, 0 as a vector. And again, this vector represents the location of this point in C coordinates using the C coordinate frame. Now, before we do the matrix multiplication, let's just figure this out by ourselves. What is the location of this origin, this point in M coordinates? Well, I need to go 5 units in the negative X direction and 4 units in the Y direction and 1 unit in the Z direction. So I am expecting that I should get, my answer should be the point -5, 4, 1, right? Because X was -5, Y was 4 in the positive direction, right? Because this is the positive direction for Y, and Z, which points up, so that is 1. And now let me just show you, if I take this matrix that I've got above, so I have 1, 0, 0, -5. Ooh, let me shrink this whole screen a bit. Is this going to work? Yes. Okay, so I have 1, 0, 0, -5, 0, 1, 0, 4, 0, 0, 1, 1, and 0, 0, 0, 1. And I multiply that by this point that I have here, my point in C coordinates. So that's 0, 0, 0, 1. And I multiply this out, I get, what's the first row? So 0, 0, 0, -5, 0, 0, 0, 4, 0, 0, 0, 1, there's a 0, 1. So I end up with, if I start with a point in C coordinates and I multiply it by this thing that I'm claiming is T from C to M, then what's this? Well, it's the location of the point in M coordinates, right? It worked in this one example. And here it is written more clearly, right? To figure out what is C's origin relative to M coordinates, I just took the homogeneous transform matrix from C to M, this quantity here, and I multiplied it by the location of the point in C coordinates, and the answer that we got was, in fact, the location in M coordinates, the location of that same point. Now, it's really pretty easy to get these matrices. You'll notice here, I don't think this coincidence probably escaped most of your attention. that there's a -5 here, and there's -5 there, and there's a 4 here, and there's a 4 here, and there's a 1 here, and there's a 1 here. And other than that, this 3x3 submatrix here is actually a unit matrix. This looks suspiciously like something's going on in here. And indeed, if I figure out that the frame transformation between M and C is something like trans ABC, again, we are the most important point of this part of the lecture, or the most important part of this part of the lecture, is that we only have translation, right? There's no rotation, we're just translating. But if we can say, I moved my frame into alignment, my M frame, I moved into alignment with the C frame simply by doing a translation in the X, Y, or Z direction, or some combination of X, Y, and Z movement, then the corresponding matrix for this is this thing. So here's another problem. Let's suppose that I want to convert points from A coordinates to B coordinates, right? So I want to have a point, like here's an arbitrary point, and I know what the location of that point is using my A coordinate frame, but I actually want to know the point's location relative to B coordinates, right? And so I'm asking, what is the point transformation, the homogeneous transformation from A to B that says if I tell you the location of the point in A coordinates, I can easily get the location of the point in B coordinates. And if I want to figure that out, the easiest way to do that is to say, well, let me see if I can figure out what's the frame transformation from B to A. And in this case, let's take a look at the picture. Frame A is on the page, flat on the page. Frame B, it says, is 8 units behind the page. And there's a 12 unit distance here and a 6 unit distance here. So if I'm trying to figure out the frame transformation from B to A, and I note that the A and B x's are parallel and the y's are parallel and the z's are parallel, they have to be either parallel or the same axis, right? They could be the same axis, but there's no rotation here is what I'm saying. What is the frame transformation from B to A? How do I take my B frame and align it with my A frame? Well, let's see. X is down, and it looks like the A frame is 6 units down along the X. So I'm going to start out by saying, I know I have a trans, right? It's just translation, and I'm going to go 6 units in the X, positive X direction. And then here's the y-axis, and the y-axis is pointing over this direction, right? The y-axis points this way. B's y-axis points this way. And so to get to the a-axis, I'm actually moving in the negative y direction by 12 units. So I'm going to write -12 here. And in terms of the z in out, if I look, the z-axis here, well, frame B, it says, is behind the page. And so I need to go in the positive c direction by 8 units. So I'm going to add to this 6, -12, 8. So that's what I think I need to do, is trans 6, -12, 8 to do the frame transformation from B to A. But of course, I know that that means it's also the homogeneous transformation that would take a point in A coordinates and turn it into a point in B coordinates. And of course, if I have this trans 6, -12, 8, I can turn that into a matrix. So I have this matrix. And so I'm claiming that any point that I have in A coordinates, if I pre-multiply it by this matrix, I will end up with a location of that point in B coordinates. So let's just try it on a couple of examples. Yeah. All right. So let's do, why don't we start with the origin of frame B this time? So I want to figure out where this point is. And remember that my homogeneous transformation is taking points from A to B. So I got to know the location of this point in A coordinates. So let's figure that out. A coordinates has X pointing downwards like this. So it's going to be, so the point is going to be at -6 in the x direction. And looking at y, it looks like it's 12 in the y direction. And the z, it's 8 units behind the page in the negative, so -8, 1. So this, I'll write a little subscript A to remind myself that this is the location of my point. Maybe I'll draw my point in blue. In A coordinates, and I want to know what the location of that point is in B coordinates. So I'm using my handy dandy transformation from A to B. If I shrink, will it all shrink together? Yay. Amazing software. So let's pre-multiply by 1, 0, 0, 6, 0, 1, 0, -12, 0, 0, 0, 8, oops, 0, 0, 1, 8, and 0, 0, 0, 1. And if you multiply this out, I'm hoping you can do these multiplications. We get -6. So I can't show you two pointers at once, I don't think, can I? No. Oh, did it show you 2? Yeah, there we go. So I have -6 plus 0 plus 0 plus 6. So that gives me 0. And then I have, come on, give me 2. Yeah. I have 0 plus 12 plus 0 plus -12. So that also is 0. And I have, come on, 0 times -6 is 0 plus 0 plus -8 plus 8. So there we go. We have another 0. And last one, we got 0, 0, 0, 1. So check it out. This point in A coordinates is the same as this point in B coordinates, which is exactly what we'd expect. I'm going to erase this stuff so we can do one more example. You're going to have to bear with me because I can't get rid of that red dot there. But let's just pick one more arbitrary point and see that it works. I mean, you know, proof by example is not exactly the best form of proof, but it often convinces students. So let's take a point that's easy to find its location in A coordinates. How's about we take this point right here, which I'm going to say is just 6 units along there. So its location in the A coordinate frame is going to be x is 0, y is 6 units over, z is 0, and we have our weighting factor of 1, and I'm going to pre-multiply it by my matrix that I've got here. In fact, maybe, there we go. I won't rewrite the matrix, I'll just rewrite the point, 0, 6, 0, 1. And I'm going to multiply these two things together, and what do I get? Let's see if we can do that double trig again. So I have, oops. So I have 0 plus 0 plus 0 plus 6. So we get a 6. And then we have, did I get 2? 0 plus 6 plus 0 minus 12. So that's -6. And then we'll do, oh, come on. There we go. 0 plus 0 plus 0 plus 8. And last one. Oh, come on. 0, 0, 0, 1. So this is telling me, theoretically, that this point in A coordinates is the same as this point in B coordinates. So if it lets me shrink the whole thing again, come on. No, it's not going to let me do it. No, it's not going to let me do it. Well, let's just bring this picture over. There we go. what was the location of, let's change colors. We were working on this point, which we said was at 0, 6, 0, 1 in A coordinates, and in B coordinates, the X, the up down, is indeed going to be 6, right? Because the origin of the, can I move this over slightly? No, I didn't want to move that over. Okay, the origin of this A coordinate frame here is in fact 6 down below this one, so we have to go 6 in the X direction to get towards this blue point. So 6 down, we have to go 6 backwards along the Y, so that's -6, and 8 forward, so we have 6, -6, 8, 1. Check it out. It worked again. Pretty cool.